Come on. Okay. Um, and yeah, I imagine you're not the only one who misses in-person classes. Because uh, and last spring we were all just kind of thrust into this, and as teachers and students alike, just had to kind of figure it out. Um, and at some point, you might get used to a routine, but then it's not the best routine. And those of you who are teaching, I know at least one of you is about to switch to face to face. So I know Walker is. Chelsea, Caleb, are you switching to face also next week? Are we offering every one-on-one section face to face? Well, actually, that's not supposed to be the case because I remember when we were all discussing this during the summer that we were going to make some sections face to face, but not all of them. So I'm thinking of what's happening at I'm sure you've heard about in one way or another from like University of Alabama, um, and actually one of my doctoral students, her daughter's going there, and that um, how when they started fall semester, they were doing mostly in person, and there's been quite a few cases, and so my student's daughter was concerned that she would have to go to like whatever space they've set aside for quarantine, like whatever dorm space. But fortunately, was allowed to simply um, take classes from home, or just and not have to pick up and go anywhere. Um, so yeah, because I mean, when I talk to so many GTAs, it's like, wow, is there anyone left who's teaching online? Am I the only one who's teach online all semester long? It's like, what the heck is going on here? Yeah, um, so I'm hoping that when you make that transition, that you have cooperative students, because um, the things I see on social media are any indication. Um, you have my sympathies. So, um, okay. Um, now, but yeah, um, basically just had to throw out your old routine and and pick up another one when you make a transition between face to face and online. And now I have the online routine down. And when I do go face to face someday, probably a year from now, um, I might have to learn how to do that all over again. Um, so, but yeah, not dealing with teams would be very nice right now, or anything similar. Okay, so what I'm trying to do is strike a balance between giving enough time to do things and to get any problems done that I assign, but also keep the class moving along. So um, and that's why I push the due date back. Um, and again, this is a guideline. So what I say when I say this assignment is due on this date, I am not saying like if you don't get it in by then, 50% penalty or some stupid thing like that. Um, you know, that's for undergrad level. Um, but more like, if you're going to keep working on past that time, then I'm still going to pile up other stuff, and that's not going to be a good situation for you, and you might want to do something about that. So that's how to interpret, I guess, Lambert speak when it comes to deadlines. Um, and yes, it has happened in some classes, like upper level undergrad, especially where I do have quite a few things dumped on me at the end of a semester, and if it's something that helps the students so that they can balance everything, that's fine. I've learned to become a very fast grader, um, because it's my least favorite part of the job. Um, so, um, but what's going on with MATLAB? Anything you'd like to throw out there? Um, any problems you'd like me to talk about?
Like I keep.
I
don't know. I don't know. Okay. I feel like I keep trying to talk about number 12. So maybe it'll eventually click. I got it to where I can do it to where there's a 0 and there's an imaginary, but then I'm stuck on the negative, and I feel like there just has to be something obvious that I'm missing.
Okay. So one thing. Echo. All right. Anyhow. Terrible. Like I put myself on so we have to have something. So whatever x you pick, one thing you can tell us that since we're talking about the difference between x transpose x, like regular transpose, and then x Hermitian transpose x, where you're taking the conjugate, that whatever x you choose has to be purely imaginary, not purely imaginary. It cannot be real. It has to have an imaginary part to it, because otherwise you'd always get a non-negative real number as a result. And that's what you must have seen, right, when you chose whatever x is to get 0 or imaginary. So, so in this case, if you are, but if you have something complex, I have to be careful here because I want to make sure to not like give it away. But actually, I want to see if I have from when I had written this stuff down before. I know I typed something out about this problem in one of the previous documents, and I'm going to try to dig that up real quick. I forget which one it is, though. It wasn't last time, I don't think. And hopefully I'm not just imagining things.
Your dad was a while ago, though.
Okay, all right. So, so I'm not losing it yet.
I think I figured it out. Like that little intro was like, that was enough for me. It got a light bulb and I got a negative for good.
Okay, well that's good. All right. So the point I was going to make was that it's a sum of squares, and what happens when you square complex numbers of various kinds. Okay, well, I'm glad that I could accidentally help you. So, okay, but yeah, that's that problem is certainly proven to be a doozy based on prior experience of students. Just got an email about for game day for football. It's like, why? How? So, actually, I went to several USM football games during my first year here back in 2009, and did not go again at all until I think it was last year or the year before. I had a remote PhD student visiting, and he really wanted to go to a game, so I was like, okay, I'll go with you. And I couldn't stay the whole time, so I left. And then there were some really exciting plays down the end that in USM 1 that I missed. So, but faculty have to pay full price for tickets, and have to, if you're going to eat at all, have incredibly lousy stadium food. So hard pass. Okay, so let's see. What else you got? There are 29 problems, and I know it. There must be several left. So I've not gotten many questions outside of class either.
I was going to ask about 25, but I just got it before this class, so that was my question.
Okay.
So I'm good now.
Well, 25. Okay, so you're approaching the end. So I should probably apologize in advance for number 29, but that one is also playing with the calendar kind of thing. Okay. Okay, then and that's okay. So you've already gotten to like the graphic stuff. Okay, cool. All right. Well, in fact, what I plan to play around with today actually does involve graphics, and so I feel like I need a prop for this. Okay. So what I have here is matrix computations. So this is a textbook on numerical linear algebra, written by Gene Gollig, who was my advisor, and Charlie Van Loan, who is a retired computer science professor at Cornell. And Dr. Van Loan, he actually visited here in 2012, and because he was part of a program that SIAM runs, a SIAM Fellows program, where if you're selected to be a SIAM Fellow, what you get to do is you spend a year traveling wherever and giving a talk wherever you go, and SIAM pays for it. So that's what he was doing then. I'm not sure how they're handling that now. Well, I guess it's a lot cheaper now. People can give talks virtually. And so he emailed me and asked about coming here. So I bribed a bunch of students with lots of extra credit to get them to pack an auditorium so that he would have an audience, because otherwise we would have been really embarrassed, because, I mean, it's Charlie Van Loan. And actually, usually when someone gets matrix computations, this is a third edition. The fourth and final edition came out after Gene sadly passed away in 2007. But this is actually Gene's copy of that book. So something I was able to inherit from him after he passed away. And so what I'm going to show today is based on the talk that he gave here back in 2012. Because for the audience that had math undergrads at USM, we wanted to have something that wasn't like a research talk, but just something interesting that undergrads could appreciate. And so he told us about an experience from a class that he would teach, like pretty low level undergrads. I think it was numbered computer science 1, where they would do some things in MATLAB. And something very interesting came out of one of these classes that actually led to a research publication. So I'm going to illustrate that, and shows that there are some really crazy things that can happen mathematically, but if you dig deep into it, you can find some kind of explanation as to as to why that is. Okay, so and I've been doing some experimentation on this, messed some things up. Haven't had as much time for it as I hoped, but I'm just going to wing it and make sure that at least pick up some MATLAB and some graphics, and then we'll and actually I can send a link. When I post the stuff from today's class, I'll include a link to his original presentation where you can find out more. Okay, now, so for this, okay. All right. All right, so now I need to get my screen shared, but it'll have to be my whole desktop because I'm going to be switching windows. But okay, I also need a document to type into probably. Right. Yeah, I was playing around with this stuff like right up until the moment class was to begin. So that was unfortunate. Okay. Come on. Okay. Sorry, just getting all my stuff together here. All right, it's time for the screen share. Okay. So actually, first I'll work in MATLAB here. See, I'll make this a little bigger. Okay. Okay. So what I'm going to do is I'm going to create a new M file here. So one you see over here, which is midpoints on it, that's where I was experimenting. But in front of all of you, I want to do this from scratch because this is going to evolve a bit. All right, so I'm going to call this random P for random polygon. Okay, so I'm going to put in a script here to create some plots that will exhibit some strange but interesting behavior. So I'm going to set a number of points, not too many. 25 seems to work pretty well. All right. So, and I'm going to comment as I go. I cannot emphasize enough the importance of when writing MATLAB code of any kind of commenting on what you do. In fact, when I go to write something that's non-trivial, I actually don't write the code first. I write comments so I have for my own reference, what is it I'm supposed to be doing? Starting with the top level description of whatever task it is, and then I start refining those comments. Like I break a task down into subtasks. Like first I do this, and then I do this, and I keep refining. Still comments. There's not a single character of MATLAB code written until I break it down so finely that I might as well write the code. And I found that that approach has served me very well because it gets me to really think about what I'm doing before I paint myself into a corner by writing code that doesn't get the job done. Okay. So what I'm going to do here is I'm going to create random points. So n of them in the xy plane. Okay, so I'll create a vector of random x values. So n of them. So this will be a column vector, and then the same for y. Okay. And then what I'm going to do is, because I'm going to carry these out repeatedly, I'm going to replace these points with the midpoints of the consecutive segments. Now, so before I get into that, I'm going to plot x versus y. And I'm going to use a dash, which is a solid curve, and then also an O for a circle. I want to actually see the individual points. Okay, so first we'll see what we're starting with. All right, so there is a random polygon of 25 points. Pretty ugly because all the edges are crossing each other, but what do you expect? It's random. So what I want to do is I want to change this polygon. I want to transform it. So if you look at each of these edges, like this one right here, I want to take the midpoint of this edge, so a point right here, and make that a new vertex. And I want to do the same with every edge. So each edge will give rise to a new vertex, and then I'll get a new polygon. So what happens is if I keep doing this repeatedly, so I keep replacing each edge with a new vertex at its midpoint and obtaining a new polygon. Okay. So I can have a loop, and I want it to run forever. So I have while true. So not the best programming practice, but I'm just playing around with stuff, so who cares? Okay. So then what I'll do is take the midpoints of my x and y values. Now, here I have 25 points. Now, if I take the midpoints, like first and second, second and third, and so forth, all the way to 24th and 25th, that's 24 midpoints. But there's a polygon, so the last point is joined to the first. So I'll take the midpoints of those also. So if I'm going to take midpoints of these points in the plane, I'm just going to take the midpoints in x and y separately. So first for x, I want to, here's what I want my vector to be. So x is going to be replaced by the following. So just to get an understanding of what I'm doing, I'm just going to write it out this way. So I have x1 plus x2 over 2, and then x2 plus x3 over 2, and so forth, all the way down to x 24 plus x25 over 2, and then x25 go back to the first point, x1, all over 2. And then I do the same thing with y. Now, I'd like to express this vector of midpoints in terms of the vector x. So I could think of this as an operation on vectors. So I have x. If I look at the first term in each, that's just x1, x2, and so forth, x24, x25, plus, and then I look at the second term in each, x2, x3, so on, down to x25, and then x1. And then I'd take all of that divided by 2. But this right here, that's just my vector of x values. But what about this one? It's not x. I want to take elements 2 all the way to the end, and then the first one. And then divide by 2. So here's how I can do it in MATLAB. So I'll have x plus, and then for this vector, I can do the following. I'll have x starting from element 2, colon, and then I can go to the last element. Now, I could say 25, but I could also say n, but I can also do this. I can say end. So this is take elements 2 to the last. Be sure to stop me if there's anything I'm typing here that doesn't make sense. So that covers all of this. I still need to include the first element. So I'll put that there. Now, the reason why I have to put a semicolon here is I made x a column vector. By the way, after class, I'll post a diary as I always do, but this file will also be posted. All right, so this will take these midpoints. So by figuring out how to express this that I want in terms of vectors, I have a relatively simple expression for taking midpoints of consecutive points, and then I take this whole thing after I compute that, and I say x is equal to that. So I'm overriding x with these midpoints. And then I can do the exact same thing with y. So I'll just replace these x's with y's. Okay. So now I have my midpoints figured out. So naturally, I want to see what they look like. So I'm going to plot them like I did before. Okay. Now, this is going to keep going. Now, if I just run this as is, I actually won't be able to see anything because it's going to keep plotting and plotting and replacing itself so quickly. So I need to have it pause. This is a very valuable command when running something long, and you want to inspect how it's behaving. If I put pause, then it will stop and wait for me. And this is very important when you have graphics going on. If you have some large computational job going and it's going to plot something now and then, you will not be able to see it as it's running unless you make it stop and wait for your input. Okay. So this is my starting point. Any questions about it before I run it? So all it's doing is just replacing of midpoints and then plotting. So let's see what it does. If I didn't mess it up. Oh, wait. Okay, I want to get rid of that figure. So I want it to pop up. Okay, so there is the initial. Yeah, that's the initial polygon. Great. Ah, dang it. Okay. So now notice down here, the lower left, it says paused, press any key. So be sure to watch for that when you use pause. If it's actually computing something, if it's busy computing, it will say busy. Otherwise, it'll say pause. So watch for that. Otherwise, you're going to sit there wondering why is it not doing anything. So I'll hit. You can hit any key, as it says. Okay, and now you see the polygon is changing. Now, one thing that you might notice is as I keep going, and the polygon's assuming more of a regular shape, but look at the scales, both a vertical and a horizontal scale. They're changing as I go. Well, not right now, but in a little bit, as I keep iterating, like you see the horizontal one just changed. Okay, so it keeps changing. So what I want to do is I don't want it to keep changing. I want to choose a fixed fixed result. The other thing I want to do is, I forgot to do this. I'm going to subtract off the mean for both x and y. So that way, it's centered around the origin. Because here, it's like it's somewhere in the plane. I want it centered around the origin. So by subtracting out the averages, I can ensure that. But the other thing I want to do is, so these are random numbers between 0 and 1. If I subtract the mean, then it should be roughly between -0.5 and 0.5. And not guaranteed, but we'll go with that. So I'm going to change the axis limits to be plus or minus 0.5. So here I'm using the axis command for that. And the way you use the axis command to set the axis limits is minimum x, minimum x, maximum x, minimum y, maximum y. So axis, so how the usage, axis, and then we have x min, x max, y min, y max. Okay. So now let's try it again with that. If you have a code that's puts up plots and you want to get rid of them before trying again, close all. I find myself using this very often. It closes all figure windows. Okay. So what happens here is, okay, so there we have our random polygon. And as I iterate, you notice it's contracting. It's shrinking. So if I keep going, dang it. Stop it. At the rate it's going, it's likely to just shrink down to a point and we won't be able to see anything. So what I'll do now is after every iteration and also at the beginning, I'm going to normalize these values. So norm computes the Euclidean length of whatever vector, so square root of sum of squares. So by dividing by that, x and y will now be unit vectors. So they won't be contracting like that. And I'll do the same thing here after every iteration. Okay. Now let's see what happens. Okay. So what we find is it's changing pretty significantly. And it's starting, the points are no longer like all over the place. That something's happening to them. That it seems like it's trying to assume some shape, trying to mutate into something. So what's it going to mutate into? This gap here is because I connected like 0.1, 0.2, all the way to 0.25. I did not do anything to connect the last back to the first. So we have that little gap there, but otherwise we see its shape. So if we keep going, now it's become a nice little blob. And it still appears to be rotating, but dang it. And it'd be interesting to see, like, if we keep going, like, will this actually converge to something? Now, it's whatever happens, it's taking a while to get there. Now, but the thing is, x and y, the initial x and y, were random. So if I interrupt this and run it again, how different will the result be? With a different initial x and y. Let's find out. So here again, it looks like it's trying to mutate into some relatively simple shape. We still have that kink there, but that appears to be going away. So it looks like some kind of bean or something, but it's becoming more and more regular, in a sense, as I keep going. Notice the gap is going around. So all the points are rotating, but within the same shape. It's looking much like an ellipse. Now, what's also kind of freaky, I'm going to make the graph have be to scale in x and y. 45-degree tilt. Now, is that something that happens every time? Now, the last one was wider than this, so it's kind of harder to tell what it had in terms of a tilt. So if I do one more, okay, and again, I want to have the same scale in x and y. I gotta be careful not to hit enter too quickly. All right, so it's getting untangled. And it seems like it again wants to tilt at 45 degrees. But I want to try to get it to more of a, see if it'll assume more of an ellipse type shape. It may be taking longer than I want for it to get there. Okay, so here it's definitely a wider ellipse than before, but it still appears to have that same 45-degree tilt. All right, so here we have this totally random polygon each time, different each time. But by taking these midpoints, then we get this kind of behavior. So why would that be? Now, the last thing that change I made was to normalize x and y, and that's just because they were going to 0. But if I wasn't doing that, and if I didn't have its fixed axis limit, I would still we'd still see an ellipse. It's just that the x and y values would be smaller because the whole thing would be condensing around the origin. Okay. So, okay. So we'd like to have some idea as to why this is actually happening. So for that, we're going to take a closer look at the equations involved and the what happens when you're taking the midpoints. Okay. So So I'm going to focus on X, knowing that the same thing is being done to Y. Ah, dang it. It would help if I could type. Okay. So suppose I have okay. So this is what I have at first, and then what is transformed into okay. So first element would be x1 plus x2 over 2. And then we have x2 plus x3 over 2. And then similar here. Okay. And then finally xn plus x1 over 2. Okay. So with transformation, that takes us from here to here. I can express this in matrix vector form. All right. So I could say that this vector of the result is equal to a matrix times the original vector okay. So before that, I'll fill in okay. Now every number in here has a 1/2 in it, so I'm going to factor that out. So let's have a 1/2 out front. Okay, and then what we have here is from a first row. If we forget about the 1/2 because it's already included here, the first row will have a 1 in the first and second positions. Okay. So we'll have like 1, 1. Okay. Second row will have a 1 in the second and third positions. Okay. Might need to make this bigger. Okay, and then in the last row, we have a 1 in the first position, multiply x1, and then a 1 in the last position to account for the last point. So we have ones all the way down the main diagonal. Actually, I'm gonna make this a little bigger to more easily see what's going on. Like I want to show the second to last row. Whoops. Okay. We're just going to have okay. Ones corresponding to the second to last and last points. Something still doesn't seem right in terms of how this is formatted. Okay. I think there's some funny spacing I need to get rid of. Like, I know this is the right matrix. This edit I'm using likes to put some space, unwanted space in some places. Okay. All right, that's more like it. So we have ones all the way down the main diagonal, and then we have ones above, but then the ones above go off the edge. So we put this one down here. Now, this matrix is called circulant. Because the entries in this diagonal circle around, and there's a wraparound effect. So it happens often in problems that have periodic boundary conditions, for instance. Okay. So what's happening here is to take the midpoints again and again, I'm just multiplying by this matrix. So and we're doing this to x, and then independently, we're doing it to y also. So the x and y values are converging to eigenvectors of a matrix. This is actually something I showed you last time with the Google illustration. It's the power method. So what's happening is taking a midpoints is equivalent to performing the power method on this matrix, where the initial vector is a vector of initial randomly generated x and y values, and the power method is meant to find the largest eigenvalue and the eigenvector that goes with it. Now, it turns out that we can say more about this matrix than just the fact that it's circulant, also based on last time. It's a right stochastic matrix. And to refresh your memory as to what that means from last time, if I add up the elements in every row, it's equal to 1. Whereas last time I was playing with a left stochastic matrix where all the columns sum to 1. Now, so what do we know about a right stochastic matrix? Its largest eigenvalue is 1, and we also know, by virtue of a row sums equaling 1, is it's a vector of all ones. Because if I multiply this matrix by this vector, like on the right, that has the effect of summing the rows, and computing all the row sums, which are equal to 1. So you would just get this vector back. But the thing is, what was done to these random x and y values? So then these vectors, these x and y vectors, makes them orthogonal. Eigenvectors. So subtracting out the mean turns out to be very important in the explanation as to what's going on here. Because when I'm taking a vector of x values and I'm subtracting off the mean, what I'm really doing is I'm subtracting off the mean times the vector of all ones, because I'm subtracting the mean from every element. So what I'm doing is I'm taking my random x and y values, I'm orthogonalizing them against this. So really, so what I'm getting from power method, is the eigenvectors corresponding to the next two largest eigenvalues. And it's something I checked on before class. They happen to be complex. Actually, I could say more than that. They're complex conjugates of one another. Okay. Now, the nice thing about a circulant matrix, though, there are formulas for the eigenvalues and eigenvectors of a circulant matrix. And in fact, you can look them up. You get the formulas there. So, in fact, if we go over there, and so those formulas are there. In fact, okay, we have a section here, eigenvectors and eigenvalues. Okay, so first of all, it turns out that so here's a general circulant matrix where we have okay, so we have a certain number down the diagonal, and then there's a different number on this, above it that wraps around here. So that's what we have. So in fact, all of our C's are equal to 0, except C0 is 1/2, and then Cn minus 1 is also 1/2. Or it says you can take the transpose, so I can say C0 is 1 and 1/2, and C1 is 1/2. So I can take, so the eigenvectors come from this formula here, and here are the corresponding eigenvalues. Okay. Now, so if I apply these formulas and get the eigenvalues and eigenvectors, then I have the following. So I'll just translate all of this. Okay. So so the eigenvalues are, so C0, which is 1. Oh, sorry, 1/2 rather. Plus 1/2 times omega j. So omega j is this. That's e to the 2 pi. So I times 2 pi j over n for whatever n we have. Okay. And this is true for, okay, so j equals 0 up to n minus 1, capital N. So if I set j equal to 0 in here, I have e to the 0, which is 1, so I have 1/2 plus 1/2. So the largest eigenvalue is 1. Everything else will be 1/2 plus some 1/2 times some complex number. And that's how we're going to get complex conjugates. Here we have a real matrix. A real matrix can have complex eigenvalues, but they are they have to be complex conjugates of each other, just like because they're polynomial roots of polynomial real coefficients. Now, to understand this ellipse that we're getting, the eigenvectors from the same formula. So we have, okay. And I'll write it in, let's see, a little more trigonometric form in this. Okay. Because what we have here is e to the I something, but that can be expressed in terms of sines and cosines. So we can actually get real valued eigenvectors to go with our complex eigenvalues. So I can say cosine of 0, and then cosine of okay, so 2 pi over n, and I can keep going. 4 pi over n, and so forth, all the way down to, whoops. So then I have 2 pi times n minus 1 all over n. Okay. And then similar for sine. So it could be shown actually that the final figure that you get is actually a linear combination of this vector of cosines and a similar one that you get for sines. And what happens? So really, what's happening is by repeatedly taking the midpoints, you keep multiplying by this matrix. All the other components of x and y that have to deal with other eigenvectors, those end up going to 0. And then it's only these two components corresponding to these two eigenvectors that are left. So in a nutshell, that's why it becomes an ellipse. And what Dr. Van Loon and one of his students proved is not only do you always get an ellipse, but you also get but you can also prove that it always has a 45-degree tilt. And it's possible to figure out from the initial random x and y what the features of the ellipse will be, like the major and minor axis, for example. So this is something that that Van Loon didn't know about when he gave his assignment in his class. He just would have his students try this out. Here's a random polygon, take midpoints, see what happens. And all of a sudden, wow, it becomes an ellipse. That's kind of freaky. Why is that? So this is where it could pay off to try to understand what's happening from a linear algebra point of view. and see like, oh, this is a matrix vector product. Well, what's happening with the matrix? By understanding the matrix that's performing its operation of repeatedly taking midpoints, we can see what's going on. And you'd be surprised as to what kind of understanding you can get from picking these things apart. And unfortunately, there isn't time, and also I wasn't able to take the time beforehand to like fully dissect all this. But like I said, I will give a link to his original presentation that has somewhat more detail than this. It doesn't fully reveal the secret as to why it's always a 45-degree tilt, but it is something that he and a student published a paper on. So all the information would be in there. Okay. Now, one thing that came up when I was preparing this was I accidentally formed the wrong matrix that would not take midpoints of consecutive points, but instead it would take midpoints of, like for each one of these points, it would take the one to its left and the one to its right, so the points that preceded it and followed it in the order, and take the midpoints of those. And what would happen in that case is I would have nothing on the diagonal. I'd have ones above and ones below. The matrix would be symmetric. And also because it's symmetric, the eigenvalues would turn out to be real. So it turned out to have a similar effect. Like if I go back to my MATLAB script and just make that change. Okay. So actually, I'm going to make a copy of this. The S for symmetry. So I changed how the midpoints are obtained. So for instance, the first one would be, like for a first point, I'd go back to the last point, and then go from there. And then this part would stay the same. So I shift by 1 and by -1. And I do the same thing for Y. Okay. So each point is replaced by the midpoint of its neighbors. And if we see what the behavior is in this case, so I'll post this file also. Okay. Now, one thing, whoops, that's rather freaky is the lines between the points. So if we just focus on the circles, so the points themselves, they too appear to be trying to form a decent shape. But if we look at all this, before the edges, we were seeing a curve that described these points. So it still is. So it's still a rather haphazard polygon because of how the points are connected. So it's kind of artistic in a way. But it still appears to be converging to an ellipse, still appearing to have this 45-degree tilt. It's just that you have the points connected in a different way. So this is what happens when you have a different approach to the taking these midpoints. But otherwise, it's the same. Okay. So, does anyone have any questions about either what just happened here, or if you thought of any homework questions while you might have been tuning me out and looking at that? Because we still have a few minutes. I know, your brains are all fried by now. So let's see, as far as our upcoming classes, okay, so we don't have class on Monday, and then we will on Wednesday, and that'll be the 9th. By the end of that week is when I intend that you are wrapping up this first assignment or getting close to it. Okay, so what I'll be doing, aside from taking questions, next class is using my MATLAB playing around time to focus on the various polynomial functions that MATLAB offers, which play a small role in the assignment anyway. And that'll set the stage for what I'll start covering the following week, which will be on polynomial interpolation, and we'll learn how to approximate functions by polynomials in various ways over the next weeks. So, okay. Good luck moving everything along with MATLAB and getting this freaky tutorial out of the way. Again, let me know if you have any difficulties. Some of these problems are quite a doozy. Look forward to seeing what you all do. Okay, so I'll cut it short here. So then, Chelsea, you have 5 minutes extra to get ready for your class. And I'll stop the recording. Okay, and hopefully the video actually has what it's supposed to have now.